Welcome to So You Want to Be a PanSTARRS Observer by Sifan Kahale. Sifan graduated from the University of Wisconsin with a degree in chemistry. Performing research for the university hospitals, she was instrumental in developing 2 of the analysis procedures of the first commercial automated clinical analysis machines. She then started and was the CEO of a small corporation that designed and manufactured what we now call PCs. Dang. These were used by the university for clinical chemistry automation. This launched her career into computers and IT, eventually becoming the director for the International Training Division, having classrooms in over 20 countries around the world. In fact, her name was given to her in Beijing. Wow. She has always been involved with astronomy, having built and fully automated a number of her own telescopes from scratch. Today, Sifan handles the summit and control room computing for the PanSTARRS and is a member of the UH steering committee for our virtual classrooms and outreach. She is responsible for the IFA's virtual presence in numerous online worlds and is here today to give a demonstration on how to operate the PanSTARRS telescope using one of these virtual models. Please welcome Sifan Kahale.
Thank you. Okay, well, welcome, and thanks for stopping in. This, if I can get this on. Or just put it in the pocket. This is a virtual world. There's a number of these that are out there. We call them grids. And one of the things that I did was to put together models of different observatories that we have. First model, of course, was PanSTARRS, because that's what I work for. And these different observatories we use for different reasons and purposes in the virtual world. This is a very serious thing. The University of Hawaii, as an example, teaches about 430-some students every semester inside virtual worlds. Graduation ceremonies are held in the virtual worlds, and for the main reason that people don't have to travel back, families and everybody else don't have to travel back to Hawaii to be able to attend the ceremony. They can do it online as an avatar in the virtual world. So the PanSTARRS observatories I have put up as an example of how you control and use an observatory, and that's what I'm going to talk about tonight. If any of you come for the open house, not the open houses, one of the astronomy groups that we have here on the island will come and use the Falks Observatory for live observing. They'll get about an hour or 2 hours of time on the Falks, and anybody can come and you can suggest any targets that you want to see. And this is the Falks Observatory, and this is actually, that one is actually synchronized with the real Falks Observatory. So when the Falks Observatory opens, the model opens. When it points to a certain place in the sky, this points to the same place in the sky. It's and what we will do is I'll invite people from all around the world to be able to come in world and see this, and they'll sit in the stands over here and watch these occur. Later on, after this, I've written on the board at least 3 of the different grids that we're in, and you're welcome to take this down and sign up for an avatar. And if you do, friend me, and I'll send you a landmark where you can come and see this. You can go in and use this yourself. What I'm going to do and show today, you can do yourself. Now, what I'm going to show you is sort of the day in the life of an observer. Starting from in the afternoon, the things that we need to do to be able to prepare the observatory for use, the scheduling that we have to go through so we know what it is that we're going to do through the night, all the way to opening up the dome and the things that we need to do in order to get it ready for operations. And then we'll go and take a look at a single observation. Now, that's not what we do at PanSTARRS. We schedule this for an entire night, and it's very critical. Every single second that goes by, we have to get as many images as we can. It's a very aggressive mission that we have. So we have a couple of observers in here, and they know, they're graded almost on their performance, you know, on how efficient they are at night. So it's a very serious thing, and we're trying very hard to do it. So with this in mind, By the way, the sky that's in here is synchronized to the real sky outside here tonight. So if you were to look at this and then go outside, if there's not too many clouds, you should be able to see exactly what you see here. So when we tell the telescope to go to certain coordinates, you can take an amateur telescope or one of these other ones and go to the same coordinates and find the same thing. This is all real. It's a simulation, but it's all reality-based. Okay, so with that, let's come down and start. This is me. So welcome to Sifan Shan. Oh, geez, she picked the same outfit as I did too. I don't understand. Anyway, so I'll give you a quick tour of the observatory, and if you've been up to PanSTARRS, you'll see that this is sort of close. So there's a little bit of poetic license involved here as I built this. This is our kitchen. Of course, I think as the observers will say, they wish their kitchen was, was quite as nice as this, clean that is. In fact, it looks, oops, let's go back here. It looks like somebody forgot to bring out the garbage. Oh, geez. I got to talk to them about that. I don't know. This is the support building itself. Down underneath here is level 0 of the PanSTARRS 1 observatory. Actually, behind my back, if I went the other way, that's PanSTARRS 2 under construction right now. In here is the Summit computing room. And I've got a number of computers in here that not only control the telescope and the observatory and the environment of the observatory, but it also handles the data flow. I think as Joe was talking about earlier, this is a 1.4 gigapixel camera. That's like 150 to 200 regular cameras. And we take a picture almost every 30 to 60 seconds. That amounts to about 2.4 terabytes of data a night. That's a tremendous volume, and all of this has to be pumped down the wires to get back down here to Kihei, where we actually do the rest of the processing on it. So my computers that we have up here basically store that as well as control the observatory itself. So let's go out in the observatory. And if you've had a tour up there, you will recognize, oh, it's hard to climb at this altitude. So we'll open the big door and come in. These are low-level device controllers for the telescope. And I apologize if this is swinging around too fast. Now, one of the things that we have to do before we ever start up is we have to go through the observatory and take a look and make sure that there's no puddles laying around, that nothing is leaking, nobody left any tools on any ring beams, that kind of a thing. This is the ring beam right here, and the entire observatory rotates on this. It's a 5-story building, and it's rotating on these wheels right here. Now, you can imagine you can't leave something in that track. That would be sort of bad. Nothing like a 5-story observatory rolling down the hill at night. It's not cool. So we want to take a look around and see if there's anything left, that's on this ring beam. And what? Uh-oh. What are you guys doing? I can't you get your check. Oh, this must be somebody else's. Okay, let's take that off of there. Oh my gosh, good thing we did this inspection. Okay, this is the fourth level, counting U.S.-wise. It's all called level 3. European level 0 is the is the first one. They don't count the first floors. So underneath here is the telescope itself. Now this is a work in process. So right now they're just represented as boxes, but eventually this will look like the actual camera that's underneath here. This is the bottom of the telescope itself. This is the shutter, so this is what's going to open to allow the picture to be taken and closed. Underneath here is the filter assembly. There's 6 different filters that are inside of here. When you have a camera this big, you want to use every single pixel that's in there. That's very important. Your camera that you have at home sort of cheats a little bit. All cameras are black and white. All digital cameras are black and white. So if you want a color picture, you have to take a red picture, a green picture, a blue picture, add them together, and that gives you your color. Well, you don't want to sit around and wait for your camera to take 3 different pictures. So what they did is they took your 9 megapixel camera, that's sort of standard. And what they did is they took every 3 pixels that are in there and they painted one red and one green and one blue. So you think you have a 9 megapixel camera? You have a 3. Okay? We don't want that. We have 1.4 gigapixels and we need every single one of those. So instead what we do is we wait around. We throw a green filter in, a red filter in, and a blue filter in, and then later on during the day we'll process this. Now, that would be okay if what you are doing is taking pictures to look at. I'm sad to say we don't do that. In fact, the only time that we see any pictures or put something together that you can actually see is when we do something like this for PR. And that probably only happened about a dozen times in the 5 or 6 years that we're here. Otherwise, all of this is data. All of this is numbers. There's no pictures. Now, I'm an amateur astronomer, so I don't like that. I like to see things. So one of the pictures that we took made it to the APOD, the Astronomy Picture of the Day. That's a high honor. And that's the one I'm going to pick on today as we take a look at this. So let's go around to the other side. Next to me over here is an FCU. That's the air conditioning unit. So here we see the telescope itself. Let me try and zoom up on it a little bit. And I'll open up the mirror covers. Oh, I have to take the lock. Because this is remotely operated, we have a lock facility that goes along with this so that one person takes a lock and then nobody else can run this. You don't want somebody else moving your telescope when you're taking images or playing around with it. So one person at a time has this. So the light comes down in through here. It comes down to the main mirror assembly, which is down here at the bottom. From here, it goes back up into the secondary mirror, which you see here. So the main mirror is going to focus this light back up to the secondary. The secondary is going to refocus it. It's going to come back down and go through this hole in the main mirror. Underneath this hole down here is a spherical lens. It's almost that large and that spherical. It needs to be able to flatten the image. Once it goes through there, then it goes down through the shutter and the filters and then into the camera itself. Now, one of the things that we need to do at night, or actually during the day before we start, is we need flats. All CCDs or all pixels are not the same. Some are brighter, some are darker. So if we want to take a look at the sky and want to make sure that everything we see up there is the correct intensities, then if a pixel is too hot, we need to subtract a little bit from it. If a pixel is too cold, we need to add a little bit to it so we get everything sort of even. So the way we do this is we take flats and we aim it at a screen in the back here, and for each of the different colors that we're going to take a look at night, we will throw in that filter, take an image, here goes the green, and then the blue, and we will save these. And then at night, when we take the images, we bring those back down to Kihei, some of the processing is going to be to normalize these pictures using that data. Okay, so that's the daytime procedures. Now let's go back down to take a look at the scheduling piece that we do during the day. There we go. Now the next 3 slides we usually have up on the screen at the same time. So we watch all 3 of these at once and we go back and forth between them. We have about a dozen different missions that we're doing, different types of surveys that we're doing. All of these are integrated throughout a night. These surveys are broken down by year and then broken down by what we call an OC. And that's an observation cycle, and that's basically the new moon so full moon, I'm sorry, to full moon. Okay, so we do our scheduling from full moon to full moon, and for each of these OCs, we have all the different filters and the different images that we need to take. So this is sort of a map for the last OC of what we need to do, and this is sort of taken towards the end of the OC. So you can see a number of them are filled in already, but there's a lot of them over here that are open. So this is what we need to do, say, tonight. We'll take a look at this, and we've got a list of all the things that we need to do. So this will show us where it is and what we need to take. The next piece is the scheduler. So this is what actually selects these. So once we find out basically what we need to take, we'll select that in this tool, and this puts it together sort of in a stack that's going to go through the night. But another piece of information we need to know is what is going on in the sky. Where is this actually moving the telescope? All of these lines are where the telescope is moving, and each of these are what we call a chunk. We do everything in chunks. So a chunk is about 24 to 30 images. Takes roughly half an hour to run a chunk. So we'll schedule by chunks, okay? And that's what you were seeing in the last couple of slides. So for instance, on this particular diagram here, this is the sky. This is what we call a keyhole. That's straight up, and that's a very difficult place for our telescope to look. We can't look straight up. Instead, remember, the Earth is turning, so it's sky looks like it's turning. So what will happen is, for instance, this chunk right here, that's getting real close to the keyhole. In fact, that's a little nervous. So what we'll probably do is wait until the Earth turns enough, or the sky moves over, and we'll take it over here. Okay. This chunk over here, if you notice, here's the moon, and we have diagrammed here the angles away from the moon. And we can't get too close to the moon because the moon's going to be very bright, and we can't take very good pictures with this. So you see, this one here is within that. So I'm probably not going to be able to take this tonight. I'll have to wait until another night to be able to take that. Instead, I'll have to go back to the previous slide and the previous instrument and come over here and pick another one that's off in that particular area. Another thing that's going on here is you see this long slew. That takes time. Remember, this is a very aggressive schedule. We have to take so many, so we won't do that. We'll go back and pick one that's back in here someplace, maybe halfway to this one, okay? Just so we can speed things up, because slowing is one of the hardest or longest things that take the longest time. So once we put all this together, this creates a key file for us. And this is what we give to the computers that actually run the telescope. And in this case, you can see here at the very top here, we're setting the Y filter in. Let's see, other things, the telescope, we're telling it to move to the right ascension of 286 and a declination of -22. We're going to set the camera to take about an 80-second exposure. The mission that we're on, this particular one, is a 3-pi. That's a survey of the sky. And finally down here, you come and say, do it. Okay, so this times 30 for a chunk times, well, let's put it this way, there's about 600 images or so that we take a night. Okay, so, and this then is what we feed into the computers that I just showed you in the previous one to do what we need to do. Okay, at this point, I think it's getting dark out, so I think we should go and start opening up the telescope. So we'll go through the opening procedure. I already took the locks, so that should be cool. So one of the things we need to do is turn off the lights. It's sort of not a nice thing to do when we're up there at the summit to have our lights on for everybody else. We will open the vents themselves. You see those black things there. This will allow, there's 4 of these all the way around. This will allow air to come through and cool down the camera, or I should say, the telescope and everything else. We need to have the exact temperatures outside, because if it isn't, there's a lot of metal in here. And as it starts to come down to the temperature, parts of that metal are going to shrink faster than the other parts, and it's going to tip our mirror, and we're not going to get a good image. So that's the other thing, besides having an aggressive schedule, we have to take good images. So it gets complicated after a while. There's a lot of these kinds of things that you have to keep in mind all the time. Okay, next thing we'll do is open up the dome itself and the dome shutters. And from before, we have the mirror shutters already open. And the next thing, we don't need the air conditioners anymore, so let's turn those off. By the way, that's our single most expensive item during the day is the air conditioning. We spend more on that than anything else. And the sole reason for that is to keep all of this metal and everything that's in here as close to what we think the temperature is going to be tonight as possible. So when we open everything up, it'll take less time for it to equilibrate with the outside. Again, image quality, and at the same time, the aggressive schedule, because we want to get on that as fast as we can.
Let me just ask again. Now, is this actually happening, and you're actually doing this?
Not in this case, no. We've got a couple of observers in the back, and they'd probably be throwing stuff at me if I tried it. This one is not. Just when I first started, there was a Fox that was over here. That one is connected with a password and a lock. So on the Fox, yes, in world, I can control it. So I sign up and get time on the schedule, and I can go in and actually run this. This particular one, the PanSTARRS, that is, yes, it could be. No, I'm not. It is possible. Okay, so the air conditioners, and we've got that turned off. Now, one more thing that we need to do before we can start operations, and we have something down here which we love to call the hurricane fans, because when you turn them on, it's like a hurricane. You don't want to stand here, you don't want to park your car here, and the idea of this is it's going to suck all that air down the dome, through the doors, and out into the parking lot. And that way it's going to cool it off much faster. And again, aggressive schedule allow us to be able to get in and do our job faster. Okay, so with that, we're open, we're ready to go, we've got a schedule. However, we don't want to sit around and wait for 30 minutes as it goes through an entire chunk. So I'm going to pick something else, and we already talked about that. It's the Trifid Nebula, and that's M20, I think it's NGC 6514. This is the one that we had published in the APOD, the Astronomy Picture of the Day, which again is a high honor. So the first thing I did was went to Google and just Google it, and this is what it looks like. That's pretty. This is a stellar nursery. Stars are being born here. So, next thing I did is I went to Solarium, which is a free program that you can get down, and just took a look at where things are. Now, it's a little hard to see, but here's Maui's hook, otherwise known as Scorpio. Here's Sagittarius. You can see the cap, and here's the little spout of the tea kettle. And if you look, you can tell I'm an amateur astronomer because this is what we do all the time. You try and line things up visually on the sky so you know where things are. So you can take the two stars of Sagittarius and draw a line out this way. Take the hook of Maui, take these two right here and draw up. And where those come together, I take my amateur telescope and just swing it right on there. Okay, that's how we work. So when we take a look at this in the sky, that's where we need to sight it if we were doing this. By the way, I've talked to some of the amateurs out there, and they told me that they will sight this. So if we have less clouds over in the south, you can go out there and ask them. So say, I heard the Trifid's up tonight. Yes, it is. Right over about there. Okay, now our telescope is an azimuth telescope, azimuth altitude. You saw the ring beam. That means that if I have a star over here that I want to take a look at, I have to turn the whole building over to look at that. So the slit is looking that way. Then the next thing I need to do is lift the telescope up to however high this is. So I need to convert RA dec, which is how the celestial sphere is calibrated, if you wish. It's in right ascension and declination. And that's going to depend on the time, okay? So you take that and the time, put it all together, and you figure out where I'm supposed to point. I cheated and went to Solarium. And Solarium says, oh, by the way, right now, let's see, what time is it? Okay, 17 minutes ago. Okay, 17 minutes ago, it was 189.45. Okay, so let's go and do that. Oh, wait, before we do that, we better take a look at the sky tonight. Now, this is actually, let's see if I can get it. Ah, good. This is real live shot of our all-sky cam at the summit right at this moment. So in other words, it looks pretty. So we don't have any clouds. That is gorgeous. So let's go back up and slew the telescope over. So we said, we'll do a slew, and we said that was 189 at 45. I also have to set something called a rotator. I'm not going to go into that right now, but I'm going to set it to 90 degrees. It's going to slew around, and by the way, if you take a look generally where it's pointing, here's the teapot. Here's our other one. So our laser beam should hit right about there. Now let's come back down. So now remember, I have to take a couple of pictures. Right, if I wanted a color picture, I need to take a red, a green, and a blue. Okay, so let's go ahead and do that. Yeah. Well, before I do that, by the way, this is hard to see, but you see this picture right here? You can barely see it. That was that flat that we took inside the dome. And you can see, you can't see very much, thank goodness, because that means it's pretty good. But you can see there's some purple and a little white and things over here. Those are bad pixels. Or those are pixels that we have to calibrate. So, okay, filter, let's take a red. Camera, let's give it 5 seconds. It'll be longer than this, but... and it's hard to see, but the laser beam is coming out, and yeah, it's hard to see that. I already took the picture. If I come down over here, we might be able to see it better. Okay, that was our red. Let's take our green, and you can just barely see the laser coming out of there. And I do that. I mean, we do not have a laser. That's a poetic license, because otherwise how would you know it's taking the picture and where it's pointing? So I built that in just for this model so you could tell what's happening. And then the last one is the blue. Again, in 5 seconds. Okay. And each of these images, you see we're taking it in the proper color. And if you take a look, you know, we have something right here. That's the nebula, okay? Okay. So the next thing we want to do is process that image. So we need to, you know, take the flats, subtract it from the actual images themselves, register the images so they line up properly, and then add them together. And you'll watch this occurring down here. And there's our image. Now, let's go back inside. Again, this is sort of what a raw image looks like. And you can see the massive number of, by the way, these aren't all the, each of these little squares, I can't remember, is that 64 by 64 pixels, something like that? So each of the squares, is the tiny squares are 64 by 64. This is huge. Okay? And this is the picture that was put in the APOD, in the astronomy picture of the day. Now, I want to show one other thing. You notice all these lines. So I can't just take 3 pictures. I have to take a picture, then I have to move the camera over, take another picture, then twist it a little bit to take another picture. This picture required 64 images to be able to put together. Okay. So there you go. Thank you. And again, if you are in a virtual world, any of these, Second Life, InWorlds, Metropolis, each of our monthly talks, you see me back there, that's what I'm doing. I'm not only broadcasting this to the web, but it's broadcasting into these locations as well. And we'll have about 30 to 50 people that come and watch this. So if you're in Worlds, look me up. If you're not and you want to, I put some of the URLs up here where you can sign up. All of the avatars are free. And say hi to me, friend me, and I'll help you get started if you wish to. And certainly I'll give you an LM to come to what I just showed you. Everything here is open for anybody that's it's in the virtuals to come and play with. So you can play with what I did here. You can go through. I've got a number of other exhibits in here as well. The Falks Observatory is there. No, you cannot control it. But you can see what they're doing right now. You can see where it's pointing and the pictures that are coming down. So again, thank you very much, and enjoy your night. And oh, by the way, go out and see the tri-shed. Okay.